Number 2 on the polynomial review says, consider the following polynomial. Circle the 2 statements below that describe the end behavior of the polynomial. So we should be able to tell just by looking at this end behavior. This is in standard form, and if it's in standard form, you look at the leading term, the one with the highest degree. And you see 2 things. You look at 2 things. Number 1, you've got this odd exponent. So if it's an odd exponent, you know that the arms at the end are either going to go, they're going to go in opposite directions. So they're either going to go this way or they're going to go this way, but they're going to be opposite of each other. And then you look at the coefficient in front, and if it's negative, you're going to have a decreasing function. If it's positive, you'll have an increasing, like sort of end behavior increasing. So here we've got this negative, so we know that the end behavior looks something like this. So now you just need to put that idea into math terms. As I go left, the function goes up. That means going left as x goes to negative infinity, so looking at one of these, y goes to positive infinity, so this one. So as x goes to negative infinity, y goes to positive infinity. And then here, as I go to the right, I'm going down. So as x gets bigger, or x goes to positive infinity, so one of these, y goes down to negative infinity, so this one. How can you determine the end behavior just from looking at the equation? I just explained that, so you figure out how to put it in words, but it's got to do with this leading term. Look at the exponent to tell which direction, if the arms are going to go the same way or different. Look at this to tell if it's going to end up as decreasing or increasing over here, right? I'm going to skip to number 4 really quickly because that also deals with end behavior. Well, I'll do 3 and 4. Okay, 3, what are the zeros of the following polynomial? So this deals with zeros, and then this one's zeros and end behavior, so we'll do them all together. So 3, what are the zeros? So remember, zeros, if you have it in factored form, so the nice thing is this was in standard form, which was perfect for telling end behavior. This is in factored form, which is perfect for telling zeros. So you just set each factor equal to 0. 2x minus 1 equals 0. 3x plus 2 equals 0, x minus 1 equals 0, and x plus 5 equals 0. So we have 4 zeros for this function, and then you just solve. So I've got 1 0 at a half, solving this one. I've got 1 0 at x equals negative 2/3. Solving this one, I'm adding 1 to both sides. I've got 1 0 at x equals 1. And here, 1 0 at x equals negative 5. So my 4 zeros, 1/2, negative 2/3, 1, and negative 5. So this one combines those 2 ideas and has you go backwards. It's telling you the zeros, it's telling you the end behavior, and it's asking you to sketch a graph. So I'm going to just use each box to be one space. So I put a 0 at negative 1. I put a 0 at 3 because remember, zeros are the same thing as x-intercepts. Zeros are where the function crosses the x-axis. And then I put 1 at 6. So now I'm guessing this is going to go up and down and up again, but it might also go down and up and down again. So what we need to do then is we need to look at the end behavior to tell which one it does. And this end behavior right here says, well, as x goes to positive infinity, that means to the right, y goes to positive infinity, and that means up. So I know I'm going to have a graph that goes up like this from there. And here, the end behavior as x goes to negative infinity, that means to the left, y goes to negative infinity. So that means as I go to the left, I'm going down, left, down. So that means my graph is going to go like that from here. So from there, we can guess that it's going to go something like that. We don't know how high or how steeply it goes, but this is a good sketch of the graph based on that information.